And this is my 1211 Lab 1 constant velocity. This is a brief overview of what I'll be going over in my slides, like an introduction, a tracker analysis, computational model, a graph, and a what-if discussion. First, I'll start with some key concepts of the lab, such as Newton's first law, which states that an object at rest will remain at rest and an object in motion will stay in motion at the same velocity unless acted upon by a net external force. We're looking at constant velocity in this experiment, and the constant velocity of an object suggests that the net force on the object must equal to 0, which relates back to Newton's first law. And formulas necessary to conduct this experiment were the velocity update formula, which allows us to find v final, which we can then use v initial and v final for the position update formula with v average to find the initial and the final position of where the object has moved. Since we're looking at constant velocity though, these values should all be the same. And in this experiment, we measured the motion of an object. We used a dry erase board cleaning spray at a constant velocity and observed this data. We put our video into Tracker and used those observed points to create a chart. We also created a computational model of the object, which predicts its motion with a constant velocity. And the purpose of this lab was to examine the observed and predicted values, comparing them to identify any differences in the data, and then to question maybe why these differences occurred. It's also important to note that we're only focusing in the x direction as the object is only moving along the x-axis. And here's more about the system and the surrounding as the system. For this experiment is the dry erase board cleaning spray, which was the object in motion that we were observing, and the surrounding is other things in our environment, such as the initial push we gave it, the table, the air. And also key assumptions of this lab is that air resistance and friction did not act on the object, but from the results of our experiment, we're unable to really make this assumption anymore, as there were other net forces acting on the object as the velocity did not stay constant, but we will go into this later in detail. And this is a video of our tracker analysis that we used for observed values. And this is part of our computational model. This is the initial conditions. I didn't change the system mass as it didn't really affect what I was using, so I left it as 1, which was what it was given to us as. We also had to put in values for our system initial position and initial velocity, which I also got from the tracker analysis I did in the first points that I was received. For the velocity though, I did use an average value I found using the 20th value and the first value to try to find an average that would match the constant velocity of our observed data. For the time, it started at t equals 0, the time of the video, and then delta t I used as 1/48 because I had 48 different stamps in my tracker analysis. Into the computational model, this is more code that I used to update the velocity and the position using a while loop, and I put my t up to 1.6 seconds as that's the time of the video. Fnet we left as 0 as we're assuming there's no net forces acting on the object. And then we applied momentum principle using the velocity update formula and the position update formula that we looked at earlier. And in the table down below, you can see the comparison between the coded of that formula and the formula written out. And then we also had to update the time to update the object's track. Versus predicted graph, which what we see is that it stays very similar in the beginning, but towards the end there is a divergence between the values. We see the observed starts to slope off, suggesting that the object speed did decrease, and this is likely due to air resistance or friction acting on the object. If they were flipped, even if they were flipped, the data would still show the same relationship. It would just the direction of it would be flipped. Instead of a positive slope, we would see a negative slope, but we'd still see that divergence relationship at the end. It'd still tell us the same information. And is it possible to say how many pushes and pulls are being added together to give a net force in the case observed? No, we really only know about the normal force and the gravitational force that it cancel out, but we cannot confirm that any other forces are canceling each other out. We do see that friction and air resistant forces are acting on the object as the speed does decrease, and there's potentially others, but we're not sure, so we cannot say that they cancel out. And in our experiment, possible sources of error could also have been maybe mathematical errors in finding our v to use for the computational model, maybe not cropping our video enough or putting it in tracker incorrectly. Those are some possible sources of our error. And thank you for listening.